if you have to perform tuning or the hyperparameter optimization of your codes, or like the, yeah, so the machine learning algorithms, whether it is random forest, XGBoost, neural network, support vector machines, there are a lot of hyperparameters that we need to tune. And Optuna, so there was a library which is called HyperOpt. So there are many frameworks which you can follow. So HyperOpt was the most popular framework before Optuna came into picture, and today Optuna is used by by a lot of places for hyperparameter optimization. And it is okay. So it's got a very, yeah. So it's got an easy to understand API, and these are the following features or functionalities that Optuna has. It's lightweight, versatile, platform agnostic, Pythonic. It's got Pythonic search spaces, efficient optimization algorithms, easy parallelization, and quick visualization. So we'll go through the basic concepts. So you have to understand two terms here. One is called the study, another is trial. So study is the optimization based on an objective function, and trial is a single execution of the objective function. So in Optuna, we will define an objective function, which will, so our entire model, be it a neural network model or support vector regression, support vector classification, anything, you have to define under a function. It's called the objective function, and you will have trial as the argument. So the goal of the, so we have study and we have trial, and the goal of the study is to find out optimal set of hyperparameter values. So for example, classifier and svm underscore c through a multiple number of trials. So it's like you can think it of as you are trying different numbers, right? You are trying different things out, and you have to define this parameter n trials. As many you give, that many number of trials will Optuna try. And this is designed for automation and the acceleration of optimization studies. So as a first example, you import the basic things in Optuna, and its associated imports you define, and then we have the objective function. So you can see that trial is the argument of the objective function, and with trial, so the trial class has got various functions, right? So these you will basically define based on whether it's a categorical. So whether you want a simple classifier. Okay, so what is the classifier? Whether it is SVR or random forest. And so you can also use an if else. So the objective, in the objective function, it is so in a particular trial, your the Optuna will choose, let's say, the classifier as SVR. So then it will run this piece of code. In another trial, if it selects random forest, then it will pick up this piece of code. So if it is, so for example, if the regressor name is SVR in the fifth iteration or in the fifth trial, then you will define other hyperparameters. So regressor name is a hyperparameter here. SVR underscore C is a hyperparameter. So we define this hyperparameter as using suggest underscore float. What is the name of this hyperparameter? SVR underscore C. And you define it from 10 to the power minus 10 to the 10 to the, up to, from starting from 10 to the power minus 10 and ending at 10 to the power 10. And whether you want to take the log of these numbers, yes, we want to take that. And then when you define the your regressor object, so we are defining from sklearn. So you will just say sklearn.svm.spr. So typically you will give a value of c. Okay, so c is a hyperparameter in support vector regression. So you will give a value of c. In this case, you will give it as this svr underscore c, which is an object of the, so which is defined using trial.suggest float. So Optuna will basically try different values of this hyperparameter, and it will give us the most optimum value of this hyperparameter. Then we have so if your regressor is not support vector regression, if it is random forest, then random forest has this hyperparameter max depth. So your max depth, so we use suggest int. So suggest int will basically just take integer values, okay, and going starting from 2 and up to 32. So now when you define the regressor object, so you will just say sklearn.ensemble.random forest regressor max depth equal to rf max depth. So typically when you are manually uh, making this model, when you're manually making the random forest regressor, you will just give some value, some number here, 5, 10 you can give. And then we will so we load the data sets. This is loading the Boston data set, and then you perform train test split, and you can say regressor object dot fit x train comma y train ypred equal to regressor object dot predict xval. So this will give you the predicted, and then we will compute the mean squared error, which is computed between yval, which is the actual ground truth value, and ypred. So this is a comparison between these two. uh, we will give us the mean squared error, and we will say return error. So this is the number which is basically something we are trying to optimize using Optuna. So the objective function having defined the model, and you get the error function, and you return the error from that objective function, so that Optuna knows what to optimize or what to minimize or maximize. So now we will create a study. So we'll say study equal to Optuna dot create study, and then you just say study dot optimize objective. So you have the objective here, and you give the end trial. So how many times, how many trials you want. Now there are so Optuna library has got these different components. We will see them, each of them one by one. So you can install Optuna by pip install Optuna or conda install. It's available in the channel Conda Forge. And then if you are okay, so this is a general introduction to Optuna, and we will see the this tutorial step by step. So Optuna is entirely written in Python and has a few dependencies. This means that we can quickly move to the real example once you get interested in Optuna. So we'll start with the quadratic function example. So usually Optuna is used to optimize hyperparameters, but as an example, let's optimize a simple quadratic function x minus 2 square. So first of all, you will import Optuna, and then in Optuna, the conventionally functions can be optimized, uh, are optimized, and they are named objective. So you will create an x which is of the type trial.suggest float. So this is a range of floating point numbers from -10 to +10, and you give the name of the variable here in string. So what do we want to optimize? X minus 2 square. So this function returns the value of x minus 2 square. Our goal is to find the value of x that minimizes the output of the objective function. And this is the optimization. So during the optimization, Optuna repeatedly calls and evaluates the objective function with different values of x. A trial object corresponds to a single execution of the objective function and is internally instantiated upon each invocation of the function. The suggested APIs, for example, suggest float, are called inside the objective function. So here you can see inside the objective function, suggest float is called, which selects the parameters uniformly within the range provided. In our example, the range that we give is from -10 to 10. Now to start the optimization, we create a study object and pass the objective function to the method optimize. So we have already seen this. You create a study object and then you do study.optimize. You pass the objective function here and say n trials equal to whatever 10 or 100 or 1000. You can get the best parameters. So after this runs, you can get the best parameters by this study.best parameters, and this will give you the best whatever the hyperparameters we have. So in this case, we have the hyperparameter as x. So the best params x, we can load that, or we can extract the value using this string that we had defined here. So what is the best params? So it gives us found x is 2.0044. So basically where it will be 0, we know that, right? If x equal to 2. So that is the value of x where this will go to 0. You increase the number of trials, and this will further have further tend towards more towards the number 2. So we can see that the x value found by Optuna is close to the optimal value of 2. Now, when used to search for hyperparameters in machine learning, usually the objective function would return the loss or accuracy of the model. So here we have seen that it is returning some number, but generally in machine learning it will return the loss or accuracy. And we have seen these terminologies, which is trial, also which is a single call of the objective function. Then we have something known as study, which is the optimization session, which is a set of trials. And then we have parameters. So these are the variable whose value is to be optimized, such as x in the above example. And in Optuna, we use the study object to manage optimization. So method returns a study object. So we have seen here create study, it returns a study object. A study object has useful properties for analyzing the optimization outcome. To get the dictionary of parameter name and parameter values, you just say study.bestparams. Now, to get the best observed value of the objective function, so what is the value of this function x minus 2 square? You just say study.best value. And to get the best trial, so at which trial, if you want to know that you got the best outcome, so you can just say study.best trial, and you can see here you will get at what trial you got this best value. So number, which is 79. This is the value of the objective function. This is the date time start, okay, date time complete, and this is the parameter that you get, okay. So and some other numbers. Okay, so now to get all the trials, you will just say study.trials. And so we instantiated 100 trials. So length of study trials will give you 100. Now by executing the optimize again, we can continue the optimization. So you can again optimize, and this will basically carry forward the previous optimization that has taken place. So it's an accumulated learning. And to get the updated number of trials, so you can see now our number of trials has been updated to 200. As the objective function is so easy that the last 100 trials don't improve the result. However, we can check the result again. So you can see here, we can we check the result again, and we are getting something similar, right? 2 point, we get 2.044. Okay, somewhere in the later on in the decimals the numbers are changing. Now Optuna has got a Pythonic search space. So for hyperparameter sampling, Optuna provides the following features. So the first is Optuna has got this suggest categorical function, which is for sampling in the categorical space. It has got suggest int for integer parameters and suggest float for floating point parameters. So with optional arguments of step and log, we can take discretize or take the logarithm of integer and floating point parameters. So you can basically choose from the optimizer. So you can, we don't know, right? Different optimizers are there. Which one, based upon the different hyperparameters, the model will performance will change. So you can have, if you so the categorical parameters, hyperparameters can be the optimizer. We can choose momentum, SGD, Adam, the integer parameter, so which is the number of layers. So you can choose from 1 to 3. And so what should be the number of channels? You can say, okay, so this is also int. This will number of units, number of hidden units, the dropout rate. So but dropout rate will be a float number, so we use suggest float, which is from 0 to 1. And then we have the learning rate, which is also a floating point number. So we ask for all the numbers from 10 to the minus 5 to 10 to 1e minus 2. And then you have this drop path rate, another hyperparameter that you can use. So how to define these parameter spaces? In Optuna, we define search spaces using familiar Python syntax, including conditionals and loops. So we can use the conditionals if and else. We can use the loop inside the objective function. We'll see how to use the loops. So with loops, you can basically make the number of layers as dynamic. So you don't need to hard code the number of layers. Also, you can use branches or loops depending on the parameter values for more. So you can, there are these examples you can go through on the GitHub page of Optuna. So for these different frameworks, you can run Optuna and see these examples. Okay, we'll see if we can go through them, but we'll complete the official documentation first. So then you can say, okay, so import sklearn.ensemble, import sklearn.svm, and we have the objective function. We define the objective function, and we have the classifier name. So this we have already seen. So you can use conditionals, that is if else, which will condition on the hyperparameter. So whether the classifier name is SVC or the classifier name is else, will basically be anything apart from, we are assuming that else is random forest. And you can also have loops in the objective function. So in this case, you can see that we create this model, or you can call it objective, this function as objective, and we define the number of layers, n layers, uh, by this Optuna using this trial dot suggest int. And the number of layers, we say that we are keeping from 1, 2, or 3. And we have this layers equal to this empty list. And for I in range n layers, so the loop will go through the number of layers, and then you don't know in each layer how many units to keep, right? So n units equal to trial suggest int. So this is the number of units. And now once you have decided, decided the number of units in a particular layer, so you will just say layers dot append nn linear. So this is the PyTorch syntax, nn dot linear in size comma n units, and layers dot append nn dot relu. So you will have a linear combination and a non-linear activation, and then you say in size equal to n units. So for the next layer, the previous layers in so the in size will be equal to the previous layer's output. So for the next layer, the in size will be the n units. And then once you are done with this, so you just keep appending the layers. So you just say layers dot append nn dot layers in size. So you basically you are collecting us in that list, in this list layers, you are basically aggregating all the layers, and then you can just say nn dot sequential star layers. So this one will basically return the model for you. Now, note on the number of parameters. So the difficulty of optimization increases roughly exponentially with regard to the number of parameters. That is, the number of necessary trials increases exponentially when you increase the number of parameters. So it is recommended to not to add unimportant parameters. Okay. So then we have the different types of optimization algorithms. So we will, so Optuna enables efficient hyperparameter optimization by adopting state-of-the-art algorithms for sampling hyperparameters and pruning efficiently unpromising trials. So these are the different sampling algorithms available in Optuna. So these algorithms basically continually narrow down the search space using records of suggested parameters. So according to you, like, I mean, you can think of these optimization algorithms to be some kind of random search or grid search. Random search is basically taking random samples of the different hyperparameters at each trial, and then coming to basically randomly trying to reach the optimization optimized or the minimum loss, right? But it's there are algorithms which are better than random search or grid search. So one of them is called tree structured Parson estimator. So this pre-structured Parson estimator is based on independent sampling, and on each trial for each parameter, TPE fits a Gaussian mixture model to the set of parameter values associated with the best objective values, and another Gaussian mixture model to the remaining value of parameters. It chooses the parameter value x that maximizes the ratio of Lx by Gx. So you can see these are the papers for the hyperparameter optimization algorithm, where the TPE algorithm. So you can see in this paper, which is titled "Algorithms for Hyperparameter Optimization." These are explained in detail. Yeah. Now, by default in Optuna, TP algorithm is used, but you can also sorry, you can also pass it as a explicitly in by using this keyword or this argument sampler. So you just say Optuna dot create study sampler equal to TPE sampler. Okay, so let us see what is there in this. Can we study this? Okay. Yeah, so then we have CMA-ES based algorithm, which is implemented in optina.samplers.cma-es sampler. So sampler using CMA-ES as the backend. So this is another optimization algorithm, and so this is CMA-ES stands for covariance matrix adaptation evolution strategy. So it's a type of an evolutionary algorithm, and you can see the way this we are trying to zero in to the uh, okay, so this star is the minima that we have to reach, And how will you reach that is basically done by this algorithm. We have to basically zero in or focus in on that point, or we have to reach that hyperparameter optimization. By hyperparameter optimization, we have to find that particular hyperparameters, or a combination of those set of hyperparameters that we reach this global minima. So you can go through this library, which is an optimization library for it says you can use this library via Optuna as well. So you can typically solve any equation with these optimization libraries. So to use this to use this CMA ES sampler, we will basically create an object from optuna.samplers.cmaes samplers, and then you create study and use and basically perform the optimization. So this is the documentation for this then, and then we have the grid search and the random sampler. Now, by default, Optina uses TP sampler as so. This we have already discussed. If you want to use different sampler, for example, random sampler or CMAES sampler, you can pass that in the argument or in the keyword sampler. And then we have these pruning algorithms. So pruners automatically stop unpromising trials at the early stages of training. That is automated early stopping. So Optuna provides the following pruning algorithm: asynchronous successive halving algorithm, hyperband algorithm, median pruning algorithm, and threshold pruning algorithm. So most of the examples will use the median pruner, and although the basically it is outperformed by successive halving pruner and hyperband pruner as shown in this benchmark. Okay. So how to activate these pruners? So to turn on the pruning feature, you will need to call report and should prune after each step of the iterative training. So you can see that we have to call this. So we have this report, and you also need to call should prune and then trial prune. So we would recommend using integration modules for major machine learning frameworks. Exclusive list is Optuna.integration, and use cases are available in Optuna examples. So you can see here we have imported sklearn.datasets, sklearn.linear model, sklearn.model selection, and then we define this objective function. So we first load our dataset iris, and these are the classes in iris. So you basically create a list of these classes, and then we get our training and validation dataset by performing a train test split on the iris data and iris.target. So now you create an alpha. So alpha is a some number which is like from 10 to the minus 5 to 10 to the minus 1, and then this is our classifier, so which is a linear model SGD classifier. Our hyperparameter here is alpha. Now for step in range 100, CLF dot partial fit train x train y classes equal to classes. So this is the set what it will do is it will just take the unique classes, unique elements. So you will just have the number of different classes, and list will create the output from set into a list. So then you report the after a partial fit, you report the intermediate objective value. So the intermediate objective value is 1 minus CLF dot score valid x comma valid y train dot report intermediate value comma step. So this is a step, like this will you will perform 100 times. and then handling pruning based on the intermediate value. So, and then from this objective function, what you will return is 1 minus CLF score valid x comma valid y. So this will the objective function Optuna will basically try to minimize this objective function, and then setting up the median stopping rule as pruning condition. So you can just say Optuna dot logging dot get logger add handler. So this is for the for controlling how the output will be displayed, and then while creating the study, you can just say pruner equal to Optuna dot pruners dot median pruner, and then study dot optimize objective. So this is the objective, and end trials equal to 20. So here you can see this is the output that would be printed. Trial 0 finished with value 0.0789, and parameters are alpha is this value, best is trial 0 with this parameter. So then you can see that trial 1, 2, 3 up to from starting from 0 up to 19. So basically 20 number of total number of trials that will happen is 20. And from the benchmark results which are available at, so here Optuna based benchmark results are present, at least for not for deep learning tasks. We would say that for Optuna dot so random sampler and median sampler, these are the best, and TPS sampler. So for the optimization algorithm, the TPS sampler and hyperband are the best. However, note that benchmark is not deep learning. For deep learning tasks, consider the table below. This table is from Ozaki et al. 2020 paper, which is written in Japanese. Okay. So this is so for we can see that for limited for parallel compute resource which is limited. So categorical or conditional hyperparameters. If you don't have categorical or conditional hyperparameters, the recommended algorithms are TPE and GPEI if search space is low dimensional and continuous. So if you have sorry, if you have categorical parameters, then TPE and GPEI search space is low and continuous. Okay. If your parallel compute resource is sufficient, then and you have categorical features, then random search or genetic algorithm are best. If you don't have categorical features, then CMAES and random search are best. So then we have the integration modules for pruning. So to implement pruning mechanism in much simpler forms, let's see if that. Optuna provides integration modules for the following libraries. So for the complete list of Optuna integration modules, see Optuna.integration. For example, XGBoost pruning callback introduces pruning without directly changing the logic of its training iteration. So this is the XGBoost based example. So you can create the pruning callback by this method, XGBoost pruning callback, which will take in trial as an input and validation error, and then just say xgb.train parameters the retrain, and then in the callbacks you give this pruning callback. So you can easily parallelize this parallelize your optimization using Optuna, and it's straightforward to parallelize Optuna.study.optimize. If you want to manually execute Optuna optimization, you have to start an RDB server. This example uses MySQL. Create a study with storage argument and share the study amongst multiple nodes and processors. So of course you can use Kubernetes. In the Kubernetes example, you can go and check this later on. This is a uh, basically how you would deal with the containerized applications. So those of you who know about Docker and containers, uh, you will find it easy to go through this Kubernetes example. So to just see how parallelization, parallel optimization works, you can see this video. And so you can create a study using Optuna create study command. So this is a terminal based command. And alternatively in Python, you can use optuna.create study. Then write an optimization script. Let's assume that FOPy contains the following code. So you just say import Optuna, you define your objective function, and you have your main code here. So you just say Optuna dot load study. The study name is equal to distributed example. Storage is equal to MySQL, uh, and study.optimize. So what you are trying to optimize is this objective function. Share the study amongst multiple nodes and processes. Finally, run the shared study from multiple processes. For example, run process one in a terminal and do process two in another one. They get parameter suggestions based on the shared trial history. So you can basically in places, different places or different terminals. Let's say you are on an HPC, you can run these optimization based studies, but since you are connected through a single database, so it will be like a coordinated optimization algorithm. So they are saying that we do not recommend SQLite for distributed optimizations at scale because it may cause deadlocks and serious performance issues. Please consider to use another database engine like PostgreSQL or MySQL. And please avoid putting SQLite database on NFS when running distributed applications. So also you can just go through this SQLite FAQs. Now you can also perform visualization of your hyperparameter optimization analysis using Optuna. So for that, we will see it's basically mostly defined in Optuna.visualization. So you can see it here. We load our model light gpm numpy, the numpy library datasets from sklearn.datasets, and the metrics. So why is this hanging? Yeah. And then from optuna.visualization, so you also first import Optuna, and from Optuna.visualizations, and this is okay. So from Optuna.visualizations, you will import plot contour, plot EDF, plot intermediate values, plot optimization history, plot parallel coordinate. So then, just give me a minute. My system is. Sorry about that. I will. Am I audible to all of you?
Yes, sir.
Yes, sir.
Okay. Hmm. Okay. Yeah. Okay, so we were talking about the Optuna dot visualization. So you can see from here, we will load all these plotting functions, and they use a particular seed so that the results are reproducible. And then you create an objective function in which you get the data, you do the train test split, and we use so in this case they are using the light GBM library. So that you can just do lgb dot dataset train x and validation x. So then you can define the different parameters: objective function, metric, verbosity, boosting type, algorithm, and you can just say what is the bagging fraction you want to keep, bagging frequency you want to keep, and the minimum child samples, and then add a callback. So you can add a callback for pruning. So this is the callback you add for pruning: optuna.integration.light gbm pruning callback. And then this callback you can add in as a callbacks to lgb.train. So then you can just say, so once you train the model, you can just say get the predictions. These are the labels, and then you can compute the scores, or you can compute the accuracy. So, and return accuracy, which is the ultimate number that we are getting from this objective function. And now you should create this study. So you run this optuna.create study, and the direction is maximize. We say, so by default it will be going, it will try to minimize the output from the objective function, but in this case we say direction equal to maximize, so that we maximize, Optina tries to maximize the accuracy. And then the sampler, that is we will use the pruner that we'll use. And then we have this study.optimize objective, and number of trials equal to 100, timeout equal to 600 seconds. So then if you just directly want to visualize the optimization, so you can see this, you can just say plot optimization history, which is you're getting from optimization optuna.visualization. So you can just pass the study as an argument. So you can see that we get we get these numbers from here. So after 80th trial, you can see that the accuracy, it jumped to the best value. So this is red line is the best value that you get after that particular number of iterations. You can visualize the learning curves of the trials. So they plot intermediate values. So this will plot you the learning curves. You can visualize the high dimensional parameter relationships. So you can say plot parallel coordinate. So we have objective function here, bagging fraction, bagging frequency, and minimum child samples. So you can see that uh, for for these different values of these hyperparameter optimizers, uh, what is it that we are getting? What is the value of objective function that we are getting? And then you can also have you can select these parameters to perform this parallel coordinate study. We can visualize the hyperparameter relationships. So the bagging fraction versus minimum number of child samples. So you can see that this is the accuracy that is plotted. So you can see the different relationship between the different variables. Okay. So select the parameters to visualize. So you can just select two parameters, bagging fraction versus bagging frequency. So you can see that here we are getting 49 and 51% accuracy. Here we got 43, here we are getting 46, 77, and here we are getting 89. Here we are getting 75, 62, and here you can see here we got 97. So this is the point that we should try to aim for. Okay, that's why we are doing this. And you can also visualize individual hyperparameters as a slice plot. So you can just say bagging fraction, the different values of bagging fraction, and on y-axis is the objective value, the objective function. So for bagging fraction is 0.6971856, the objective value is 1. Bagging frequency, minimum child samples, you can select the parameters from here. You can also visualize the parameter importances. So you can here we can see bagging fraction, it has got the maximum importance, then comes the minimum child samples, then bagging frequency. Learn which hyperparameters are affecting the trial duration with hyperparameter importance. So minimum child samples is basically contributing most to the duration of the trials. And then we can visualize the empirical distribution function. So this is the distribution function. So objective value on x-axis, the cumulative probability on y-axis. Okay. So next, you can save or resume this study with an relational database backend. Relational database backend or RDB backend enables persistent experiments as well as access to history of studies. In addition, we can run multi-node optimization tasks with this feature, which are described in easy parallelization. In this section, let's try simple examples running on a local environment with SQLite database. You can you can also utilize other relational database backends such as PostgreSQL or MySQL by setting storage arguments to the database URL. So refer to SQL Alchemy document how to set up the URL. Now we'll set up a new study. So an SQLite file example.db is automatically initialized with a new study record. So we will just import Optuna and then we will say optuna.logging.getLogger. So this is for the output. And then so we define the study name. This is the string, and we define the storage name. So which is equal to SQLite this one dot db, and the format is this example study. So then you create this study Optuna.create study name equal to this one, storage equal to storage name. So it will give you something, an output like this: a new study in relational RDB with the name example study has been created. So to run a study, call optimize method. So you can see that you define the objective function, return something which is dependent on the hyperparameters that you are trying to optimize. So you just say study.optimize, objective, and what is the number of trials. Now you conducted this study once. Now to resume a study, instantiate a study object by object passing the study name, example study, and the database URL SQLite example study.db. So you just say if load if exists equal to true, and then if you run this optimize again, it will use an existing study with name example study instead of creating a new one. So we can access histories of studies and trials via the study class. For example, we can get all trials of example study as so by this method, and you can create it. You can turn it into the database into a pandas data frame. So you can just say study.trials data frame, and what are the attributes that you want: the number, value, params, and state. So it will say this using an existing study with example study instead of creating a new one. Method trials data frame returns a pandas data frame, like, so you can print this data frame and it will give you something like this. So the number of like the trial number, the objective function value, the parameters. So here you can see the objective function value. If you're getting something near to 0 when you are having the number x near to 2, and this is the state. So a study object can also provides properties such as trials, best value, best params. So you can see study.best param, study.best value, study.best trials, and study.trials. And then you can also have multi-objective optimization with Optuna. So if you want to basically optimize two objective functions, or you have two tasks that you can do with Optuna. So this tutorial showcases Optuna's multi-objective optimization feature by optimizing the validation accuracy of fashion MNIST dataset and the flops of the model implemented in PyTorch. We use THOP to measure flops. So what is flops? Flops is floating point operations per second. You should know this. So we import THOP and the Torch library, Torch Vision, import Optuna. So then we have device is equal to torch.device CUDA if torch.CUDA is available, else we use a CPU. We have the directory, batch size, number of training examples, number of validation examples, and then you define the model. So in the model, we keep number of layers as a hyperparameter. So then you have these number of layers. Then we have the input features, in features equal to 28 cross 28. Then you will go layer by layer, and what is the number of output features, that also we will keep it as variable. That also is a hyperparameter. And then layers dot append, nn dot linear, in features, out features. So then you can just do layers dot append. So in the end, you will we want to have basically 10 nodes, and in the end we have just a single log of softmax, and then return nn dot sequential layers. So this just keeps appending all the different layers to this list layer, to this empty list, and then this will create a neural network. So then you can so we have this train model. So it takes in the model, the optimizer, the train loader, and we just say model.train. So it goes in the training mode. And for batch idx comma data and target in enumerate train loader, so data comma target equal to data.view to device. So you put this in the input and the target to the GPUs, and then you say optimizer dot zero grad and f dot nll dot loss model data. So this is the model generated output, this is the observation, dot backward. So you back propagate, and then optimizer dot step, this will forward propagate. And then similarly you create the evaluation function, which will in which you just pass the model and the validation loader. So you just say model.eval and correct equal to 0 with torch no grad. So here we should not perform any kind of update to the weights. So then similar thing, you compute the so you iterate through the examples, get the data and target, you perform the prediction, and then you basically add up the accuracy in the in this variable sum. And so the accuracy equal to correct total, which is divided by n valid examples. And then you will compute the flops, so which is floating point operations per second, and then return flops comma accuracy. So after creating the model, train model, and define model, train model, and eval model, we will create our objective function. So which is in which we first load the data set, and this is the data loader. So you basically have this train loader defined in torch.utils.data loader, and then this is our validation data set, validation data loader. So now we will define our model equal to define model trial dot to device, and then optimizer equal to torch.optim.atom. So what are the parameters in the optimizer? Although we are using the atom optimizer, but we will give the model parameters and trial.suggest float. Learning rate here that we will give to the optimizer will range from 10 to the minus 5 to 10 to the minus 1. And then we will say for epoch in range 10 train model, so we'll train it 10 times within one objective function, like one trial we will do it 10 times. And then flops comma accuracy equal to eval model comma validation loader. So this will return two numbers, flops and accuracy. And now we will run a multi-objective optimization. So if your optimization, so in this case uh, we want to minimize the floating point operations per second, and we want to maximize the accuracy. So Optuna assumes that you will specify the optimization direction for each objective. Specifically in this example, we want to minimize the flops, maximize the accuracy. So we want to set the directions as minimize, maximize. And so here you can see while creating the study, you pass this list to the directions argument. And then you say study.optimize objective, comma n trials, comma timeout equal to 300 seconds, number of finished trials. This will give you so the Optuna.visualization plot Pareto front. This will give you the plot of, so on x-axis and y-axis, the different metric on which you are trying to optimize your function, objective function. So you can see that the dark red corresponds to the best trials, and this is the number of trials. Okay. Learn which hyperparameters is affecting the flops with hyperparameter importance. And okay, yeah, so we will end this class here today. If you have